Okay. So today, I'm going to talk about. I've got it button here on both these. Okay. So today I want to talk about hypothesis testing. This, again, as I've said before, this is stuff that you've run into before. The logic of hypothesis testing is something that I know you've run into in 2126. Some of you, I taught this in 2126 using very similar slides, if not the same slides. So this is kind of a quick one today, but it's nice to get the background here. And again, we're trying to get back to a point where we're all in the same page as far as our, that's what I'm looking for, our background. Okay. So we're trying to get all back to the same place. I like that transition. I love that transition. Okay. I'm just going to move something. There's stuff on my window here that you don't have to see. It's got to get out of my way. Okay. Also make this bigger so I can see it better. So there's three things we want to say if we want to say there's a causal relationship. And what are we interested in? Why are we doing statistics? We're doing this because we want to say that X causes Y. So the first thing we need is temporal precedence. All that means is the, what's the word I'm looking for? The number, that the cause causes the effect. We don't necessarily know that all the time. Right? We don't necessarily know that all the time. So that's why we have to do the science. That's why we have to do the experiment, right? So we have to see that X causes Y. We have to say that if we design the experiment, that the cause is before the effect, temporal precedence, temporal time precedence, one before the other. We have to eliminate alternative explanations. So if I gave you a list of words and divided you into two groups. In one group, I gave, 5 shots of alcohol. In one group, I gave 5 shots. I gave nothing. And the group with 5 shots of alcohol did poorer on the number of words recalled. I certainly would be reasonable enough, I guess, in saying that alcohol causes problems with memory. But I'd also be, there's an alternative explanation there, right? That I can think of one right away. Can anybody think of an alternative explanation of why a group who's had 5 shots of vodka does more poorly than a group that doesn't have 5 shots of vodka, other than they're drunk? And let's assume I've used random assignment and the groups are the same. Any thoughts? What could it be?
I'm just thinking of like mistakes where they're maybe reading or hearing.
Sure.
I don't
know.
But
why would they make those mistakes? Other than they're drunk. You're on the right track, for sure, because that's probably what causes the problem. Maybe they have to pee. Think about that. I mean, I know it sounds crazy, but in fact, if you've had 5 drinks, and let's say it's not shots, let's make it gin and tonic, a big drink, you probably have to pee. So you get distracted. So how do we fix this? We eliminate the alternative explanation by having a control procedure rather. Like one group doesn't get gin and tonic, or sorry, one group, let's make it better. Let's make vodka and soda, right? Like something like that. So we take, both groups get soda water, but we put a whole lot of peppermint extract in them. And in fact, that works really well. You can't tell if you've had alcohol or not. And I know that from being, from people I know who do alcohol and memory research, that people think they're in the alcohol group, and even though they're not. And in fact, they act drunk. And then you tell them they're in the placebo control group and they go, oh, and their drunkenness goes away. So that's important. The final thing is covariation, that as X changes, Y changes. As the cause changes, the effect changes. Now, this is a different issue because the first two, temporal precedence and elimination of alternative explanations, we take care of those with design, with experimental design. So if you've taken Psych 2127, which I think you have to take this class, that's a class about research design. It's really boring, but important. But I'm so glad I haven't taught it since last time I taught it was 1997. Because I find that stuff so boring that I think I fall asleep while I'm lecturing. But we can deal with those two, but with experimental design. We can't really deal with covariation with experimental design. How do we really know that as X changes, Y changes? Well, that's why we do something called a hypothesis test. So I just made up some data. These aren't important. What I'm trying to take a look at here is we've got, I don't even know what they're measuring. They're literally just numbers I pulled out of the air. So we have two groups. One group has a mean of 66.2. The other group has a mean of 71.4. Standard deviation is 785 and what is that, 856. I hope those are correct. I did that with a calculator, so they're probably correct, but it could be I made a mechanical error. So it doesn't matter what these are, but let's say you collected the data on these two groups. And whatever the hell this is measuring, you can make something up. Let's say it's percentages on a test. That looks reasonable. And one group, let's say group 2 had a study method of, I don't know, making their own notes, and group 1 didn't have that. They had made up notes. By the way, making your own notes literally does show you to be better, does have a better, you do better in memory tests with when you make your own notes rather than when someone makes up your notes, including experts, by the way. Okay, so here's a question with those two groups. So again, let's just quickly go back. Remember these numbers. Whoops, we're gonna go here. Let's go back. So we've got 66.5 and a mean as a mean, and roughly 7.9 as standard deviation, and 71.6 and roughly 8.6 as a standard deviation. Those are pretty close. So the question I have for you is this. Here's a distribution, and how did I get that? I went to a website that makes distributions. Let's put that over there, make it a little smaller. Could these two sets of data come from this same distribution just by random chance? So what I'm asking you is, do these two sets of scores, could they all have come from here? I'm not asking you to do any statistics. I'm not asking you to do a t-test, which is what you'd do. I'm not asking anything like that. What I'm asking you is just intuitively. Going back, let's go back and look at these scores. We've got scores. What's our lowest possible score here? It's what, 57, and our highest one is 81. Okay, so let's go back to our distribution. Yeah, I think those could all come from this. They're all pretty much in the meaty part of this curve, like in the big part where we all normally all live. I don't know, man. I think they could all come from there. So just by random chance, not because the groups are different in reality, like in the population, but just because we just randomly have people and everybody's a little bit different. It seems, in fact, to me, extremely likely that these groups, these scores all come from this same distribution. Questions so far? Yeah, I mean, it really seems really likely to me. These scores all come from this distribution. Okay. What we've just done is we've made a decision. We've not done it technically the way we tend to do it in a statistics class, but we have made a statistical decision. It's an intuitive one backed up by a little bit of looking at a graph. But as I said, when I talked about exploratory data analysis, statistics in a lot of respects are there to prove what you already know. And we already know these two sets of data come from the same, or we're pretty sure that they could come from that same distribution. Now, do we ever know that parent distribution? No, we don't tend to know those things. That's why we have to do the science. But if we think about this from a sort of we are all knowing sort of perspective, it seems pretty likely. So we've made a decision. So if the chance is relatively small, let's go with less than 5%. We say it's unlikely that our difference happened just because people are different by chance alone. That's shorthand. What I'm saying is we're saying it's pretty unlikely that they come from two different population distributions. And so we therefore say we have a statistically significant effect. Okay. So we've just made that decision right there. Why is it 5%? Well, we'll go into technically why it is 5%, but if I was to flip a coin 10 times and I was counting heads and tails. Do you feel, I don't think anybody would say that the coin was fixed. In other words, it's not a fair coin. It's some kind of coin that I've tricked into landing on heads more than tails. Like I've got some kind of trick coin. If it landed 5 heads and 5 tails, I don't think you'd think that. 6 heads and 4 tails? No, that happens. 7 heads and 3 tails, you might start to think, but also it's not a big deal. 8 heads. 8 heads starts to get a little bit weird. You start thinking, gee, what's the chance of that happening? And it's 0.8 times 0.2 times 10. That's how many. So somewhere between 8 and 9, we can't have 8.5 flips, but whatever. When you get somewhere between 8 and 9 out of 10, people start, in fact, just intuitively saying, no, that's a fixed coin. And in fact, that's right around 5% chance. It's possible to get 8 or 9 or even 10 heads from a completely fair coin. It's just really unlikely. But it can happen. Right? It can happen. It just doesn't happen that often. And it's so unlikely that most people will go, yeah, it's probably a fixed coin. And you're probably right. And literally, that intuitive feeling we have is right around a 5% chance, of 0.05 probability. Without this statistical significance, without that, we don't really have covariation of X and Y, and therefore we cannot make a causal claim. We can't say that as one changes, the other one changes, because in fact, we're saying that there's a good enough probability that that's not what happened. So these are probabilistic statements. We are not 100% certain of these things. But the chances are way better that say X happened or Y happened or whatever, okay? This is something we've been going through in the last, well, when did the vaccines become a thing? December of 2020, they started showing up, right? And you have people saying, well, it's not 100% effective. It's the same kind of thing. It's like, think probabilistically. If it's 70 or 80% effective, that's pretty good. People have real trouble with probability. It's not an intuitive thing. And that's where people have trouble with statistics. It's not the arithmetic. It's not the math. It's not the formulas. It really isn't. I know it's easy to blame that because it's looking right at you and you see, the sum of the x's minus x bar squared, divided by n minus 1, take the square root of that quantity. You look and go, that's the thing. That's why I don't understand it. No, it's not that. Actually, it's because most people just have trouble thinking in probabilities. Probability is hard for most of us. And there's a whole evolutionary explanation of that I can get into that I'm not going to get into. But I can tell you, maybe if we have time at the end, I will. But people can't think probabilistically. We're just not very good at it. Okay. Questions or comments so far? All right. Well, then let's do the next one. Next slide. So what we do is we set up 2 mutually exclusive hypotheses, okay? We set up HO, the null hypothesis, which people used to call, so H sub O or HO, you should just say HO, the null, which is that nothing happened, that the 2 groups, let's say we have 2 groups in this case with our group 1 and group 2 example, come from the same parent population distribution. It's the null hypothesis. People used to also call it HO until HO got a different meaning. But literally when I was in undergrad, the prof would talk about HO. And you don't do that now because it means something else as well. And I don't mean a garden tool. And then the other one is HA, or sometimes you see H1. And again, my stats prof in undergrad called it HA. Ho and HA. That's the alternative hypothesis. Sometimes you'll see H sub 1. And in fact, you'll probably see me use that sometimes too. HO and HA, HO and H1. They all are the same thing. So H1 is the alternative hypothesis. That's that something happened. HO is that nothing happened. All this is HA is just that something happened. That's all. It doesn't say what that something is. It doesn't say that anywhere. We either reject HO or we don't reject HO. We never accept HA or accept HO. Anybody who says that is using a shorthand, and that's fine, but you should realize that's not really what they mean. That's not what they should mean anyway. Okay. You can see books do that, and especially like second year stats books, like 2126 books. I know that people who teach that course, me and Dwayne typically, Paul teaches it sometimes too. We tend to find books that don't say that. It doesn't end up in most books, but I have seen it in print, which makes me wonder if these people have editors. All right, questions? Anything I can answer so far? Good. Okay. So HO is the null, HA is the alternative. So we're going to make mistakes. Because this is a probabilistic thing, we're going to make mistakes. And, you could think of this right now in terms of, let's think of a COVID test, right? Because I think many of us have had these tests. And I don't mean a PCR test. PCR tests are extremely unlikely to make mistakes. I mean, the rapid antigen tests, those are more likely to make mistakes. Not a lot. They're about as reliable. They're not as reliable as a pregnancy test, but they're close. Many of us have also dealt with a pregnancy test. And depending on where you are in your life, you either are really happy with the result or really shocked and frightened with the result. Sometimes you're happy and shocked and frightened. That's where you are usually when you have your first kid. Anyway, we set up two hypotheses, HO and HA. This up here, okay, HO true and HA true, that's reality. That's what's happening in the world. We don't know it. We can't know it. Well, we could. If we knew it, would we have to go collect data? Answer, no. Here's what we can control. HO, do not reject HO. And and reject HO. So do not reject HO. This is our decision. This is reality up here. This is our decision over here. All right. So let's just say that HO is true, that you don't have COVID. And we do the rapid antigen test, and it comes up. If you've ever done one of these, it's got the C and the T. And when it's the C, I'm sorry, I think the T is the one where you don't have COVID, right? Yeah. That it comes up. Or again, if you've done a pregnancy test, whatever. You don't have COVID and you don't reject HO. You've made a correct decision. Yay. What if HO is true? So you don't have COVID, but the test comes up and it comes up at the C. You go, I think it's the C. Again, I can't remember. It's either that or the other way. Anyway, it comes up that you have it. You reject the null hypothesis. You say, oh, I think the test says I have COVID, but you actually don't. Now, you don't know that. The way you actually find out is you do a PCR test. Again, PCR tests are extremely accurate. The chance of a false positive, if it's done properly, is vanishingly small. It could happen, but it's so small. You'd have to know how PCR tests work, but they don't make a lot of mistakes. Like, if it's done in proper lab conditions, they pretty much can't make mistakes. The way you get mistakes is a contaminated sample. The test itself doesn't make mistakes. Well, it could, but again, the chance is so vanishingly small. It's just like if you think of DNA tests, they can make mistakes, but not if the samples are done properly and people know what they're doing. So this is called a type 1 error. And the probability of that type 1 error, we set that. That's the 0.05 thing. That's the 5%. Okay? That's the 5%. Now, what if HA is true? What if you have COVID? But the rapid antigen test, the RAT, says you don't. That's your statistical decision, but you actually do have it. That's called a type 2 error. That's a type 2 error. It's a false negative, right? The type 1 error is a false positive. The type 2 error is a false negative. Again, with a PCR test, that's not going to happen. Well, again, it's so vanishingly unlikely that we can just say it's not going to happen. But you might have had a pregnancy test, and the first time you took the test, it said you weren't pregnant, and then or your partner wasn't pregnant, and then you wait 3 weeks and go, I still haven't, or a month, I still haven't had a period, and I feel kind of sick in the morning. Maybe I should do another test, right? And when you do that, you make a correct decision again because you have made the decision. Sorry, you made the decision to reject the null hypothesis, and HA is actually true. So you can think of this, pregnancy tests, COVID tests, these are things that we've all dealt with, most of us, more or less. You could also think of guilty and innocent in a courtroom, right? If those analogies help you, that's great. If you want to think about this abstractly, because you think that way because you're like me, great. The world needs fewer people like me, not more. But if you can think in probabilistic statistical terms, that's wonderful, and do that. But it doesn't make it any better if the analogy of someone being, innocent and then they get found guilty or whatever. Notice how, by the way, even in a court of law, we never say people are found innocent. We say they're found not guilty. We just haven't rejected the null hypothesis. All right. Any questions I can answer on that? And again, I know this is stuff you've run into before, but don't feel like you can't ask questions about this. Okay, good. Now we do have some control in this situation. The first thing is we set the probability of the type 1 error. We actually say we're going to make the decision to reject the null when there's some very small chance of it being true. So 0.05. We usually set it at 0.05. It's called alpha. And I'm going to apologize in advance. You're going to see the terms alpha and beta, and they're used here about probabilities of a type 1 and type 2 error. And then you're going to find out later in the course that we also use those Greek letters to to stand in for other things. And that's really annoying, and don't blame me. I don't know why it's like that. I think they just ran out of Greek letters. I don't know. The probability of a type 2 error, on the other hand, we don't set. It can be calculated, but if we're going to get the probability of a type 2 error, we actually have to know the distribution in the real world. We have to know what the parent population distributions are. And that's not something we can know, because if we knew that, we wouldn't have to do the experiment, would we? But the probability of a type 2 error depends on a few things. It depends on the number of observations, that's n. It depends on the standard deviation or variance, whatever, of the distribution. And it depends on alpha, right? And this is called beta. It's the probability of a type 2 error, and that's a false negative. This is a false probability of a false negative, a false positive, I'm sorry, that's alpha. A false negative is beta. Okay, so we have some control here. And 1 minus beta is something we're very interested in, because 1 minus the probability of a type 2 error is the probability of a correct rejection. We call that statistical power. I don't know why I've capitalized that, probably because I like having statistical power, because what that leads to is publishing papers and getting promoted. So I can tell you that when I taught Lori Bloomfield, I've told you this course, geez, when was that? 1997, something like that. Then she was my TA, which is kind of great. And when I asked on a quiz or a test, it was one of the two, what the definition of power was, and she didn't know. So she wrote, the power is what Dave has over our marks. So good on you, Lori. So that's the probability. So this is a false positive alpha, a false negative beta, and a correct rejection 1 minus beta. Okay. And there's probabilities. They're out of 1. This is going to usually be 0.05. type 2 errors might be something around 0.15. And then that makes this about 0.85. That would be a really nice beta and 1 minus beta set of numbers. I can tell you in advance, we can't really know this. This is going to be a guess. This is going to be a guess. We can theoretically know what alpha is because we've actually said it. We then have to make sure that we don't violate any assumptions of statistical tests and sampling and all that. There's also, in some of the statistical literature, you'll see something called a type 3 error. So there's a type 1 error, a type 2 error. A type 3 error is you're asking the wrong question, so that your experiment sucks, basically. It's not answering the question you think it is. But that's more of a design thing than a statistical thing. So what do we set alpha at? And of course, everybody goes 0.05. It should be 0.05. It should be 0.05. Psychologists are horrible about this. It should be 0.05. It should always be 0.05. We're the worst. For years, ever since I was in grad school in the late 80s and early 90s, people have been moving away from this worship of the 0.05 level of significance, but it's still out there. And the reason we do this is because of a guy named R.A. Fisher. Now, R.A. Fisher came up with the analysis of variance. We're going to talk about the F-test. Also, almost certainly a racist, but, and I mean more than everybody was in the 20s, okay? Basically what happened is Fisher's, I think it was Tukey, we talked about Tukey, telegrammed, they didn't use, I don't mean that weird app, I mean, an actual telegram, and asked Fisher what percentage points of this distribution are your students working on, because they had to work out the probabilities using calculus by hand. And he said 0.05, and Tukey was like, okay, I'll have my guys work on the same thing. Seriously. So it's 0.05 because two guys thought that was reasonable. It's intuitively pleasing too. I talked about the coin flip and all that, but it's mostly just a weird artifact of history. I think being more flexible makes a lot of sense. Whoops. So let's say, I mean, I once ran into, I wrote a paper, as you do, and the effect I found a whole bunch of effects. They all went along with the sort of theoretical approach that I had. And they all made sense. They were all consistent. And I said that the probability of this being significant was 0.0504. That was my, in this one effect. And I was told by the editor of a journal do not discuss non-significant effects. Like, it went along with everything else I found. Had I rounded it, I actually wrote this back to him. I said, fine, I won't. This was when you write a paper, it goes to an editor of a journal, and then it goes to 2 referees or 3. And the referees talk about stuff. None of the referees, by the way, who are other experts, flagged this 0.0504 as a problem. One of them did, but the editor of the journal did. And he said, don't discuss non-significant effects. And then you reply and say, okay, I'll do this, 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 and this. And then you also usually say, but I'm not doing that. And then you see what the editor says. I did this because it was my first year of a job, right? I was an assistant professor first year. It's like, okay, well, I'll just let that go. But I did say, had I rounded this, it's 0.05. I thought I'd report this to be honest, but I won't discuss this. And I put in scare quotes, non-significant effect. Think about this. Well, actually, let's see. What would be a case be where you would be comfortable with there being more false positives than 1 in 20 or 5 out of 100? So anybody got any ideas of where you'd be comfortable, where you think it'd be a good idea having some false positives just to make sure you catch more actual effect? Any thoughts on that?
With a participant response in, like, if they're supposed to get something wrong or right, and you want the wrong as part of your data, or in any situation where getting something wrong is valuable data regardless.
I see where you're going, but I think what you're saying here is more about what data you include. I agree, though, that you should talk more, that people should generally talk more about non-significant or non-correct answers. In fact, much of my career is based on looking at errors, to the point where, and second choices people make after, or birds after they make a mistake, to the point where when I put my hand up at a conference, people know exactly what I'm going to ask. Did you look at the error rate? So you're on a track there, but it's somewhat different than this, but good. Other thoughts? Think about a situation. Well, what's one we're in right now? I'd rather there be some false positives than, people dying. So, oh no, you can't go back to work and we can't have face-to-face classes. That's better than, what could conceivably the possible ramifications are some more extra people die. When I lived in Corner Brook, Newfoundland, every single year in the spring, there was a boil order on the water, usually for about 3 weeks, because there was a possibility of something called Giardia, which is an unpleasant little bug that makes you poop a lot and vomit. Now, that's not pleasant, but if you're a very young child or an old person, you can die. You can literally poop to death, which sounds like a horrible way to die. Now, I asked actually a public health official because I was interested, and I just knew somebody and we were talking, and I said, what is the probability of a false positive? And he said about 0.15. And you know what? I'm totally good with 15% of the time they're being overcautious. It's the same thing with secondhand smoke research. Almost all research on secondhand smoke, that it causes health effects, hardly any of it ever gets to 0.05. But you know what? It all goes in the same direction. It never says it's neutral and it never says it's good for you. So you know what? I'm okay with people saying you can't smoke in buildings. Totally cool with that. Even if individual studies don't go at 0.05, all the data go that way, I'm good with that. That's fine. Same thing with boil orders. Same thing, frankly, with public health measures make some sense to me. Where's a case where we would maybe want to be really sure and say we don't want any false positives? Anybody think of a sort of a case, any kind of science, doesn't be psychology, where we would say we're totally comfortable with saying we don't want any false positives?
Pharmaceutical research.
Yeah, depending on the drug. I think you're right. I mean, let's think about something like, I don't know, what's something where, I don't know, let's say we have a drug with a lot of side effects, especially, and we've already got a treatment that works. This treatment that's coming out, I better be damn sure it works. That's a good one. That's one of the ones I would choose as well. Another one is there ESP? Are there aliens? Like, I don't want to make an idiot of myself. So I don't want to say there's only a 5% chance that the signal I found is not about aliens, that it's actually just a pulsar. Oh, now I've made an idiot of myself and I look like a fool. So, there I would want to go maybe 0.005 or 0.001. Because if I'm going to blow the lid off everything, if I'm going to change everything, I better be damn sure I'm correct. So what we're starting to see now, and this tends to be because people of sort of the next generation, away from this guy here. By the way, the guy that said this, he was the PhD advisor of a friend of mine, which is wild. Anyway, that generation, they aren't running things anymore. The generation that run things, that's me and my colleagues, we're a lot more sympathetic to the idea of let's just be a little bit more subtle, shall we? And a little bit more flexible and say, you might report your p-value. And then look, if everything goes in the same direction of 5 experiments, that's fine. So we're a little bit more flexible now, but it's hard to get through to some people. And this is nuance, and we don't teach a lot of nuance in intro stats because we can't. And that's why you didn't hear a lot about this in the intro stats course, either if I taught it or Dwayne taught it. I think I might have mentioned this in intro stats, and Dwayne may, I don't know, but isn't Dwayne May a famous guy? Anyway, Dwayne might, but I know I do. I think I do. When I teach intro stats, all I'm saying is we want to get the basics into you, and then we can get to this subtle stuff later. Any anything else? No, I don't. Any other comments or questions on this stuff? You good? All right. On that note, we will pack this one in for today. And let's see here. Whoops, it's not doing it. Oh, there it goes. Anyway, on that, like I said, on that note, we'll pack it in, and I will see you all